For the laptop you have, the connection doesn't give you the.
Yeah, I need to test it. It's like off the critical path. Okay, let's get started. Welcome back. Fridays are always thinner in terms of people who are attending. But it's still good to see an almost full room. I don't know if there are people in the other room, but I still cannot see. Maybe there are some. I don't know, you can come here. There's space here, but maybe you like the fewer people in the other room. Anyway, we're going to continue where we left off yesterday. Hopefully yesterday was exciting. Was it? Interesting? Cool? Okay, we're going to learn more stuff today, hopefully. But, okay. Before I start, I'll remind you, there's an extra credit assignment that you know. There are some readings, and I would definitely recommend you to the readings because they will help. And these are the readings that are kind of foreshadowed for the future next week. Today, what we're going to cover is build on what we did yesterday. Yesterday, we started with some basics, of course, plus we talked about transistors, We talked about transistors as a switch. I'm going to very quickly overview that. We started building logic gates. We're going to build more logic gates today. We're going to talk about Boolean algebra. Have you covered Boolean algebra before? Yeah. Yes? At ETH? Yes? Okay. I'm going to go through those relatively quickly. Maybe there are parts of Boolean algebra that you did not cover, but that's going to be relatively quick. Well, hopefully. When I say that, usually it takes time. And then we're going to jump into combinational logic circuits. Boolean algebra is useful from our perspective so that we can design circuits and also we can minimize them. We want to reduce the cost of the circuits. And Boolean algebra, both the theory as well as design tools that build on that theory will enable us to minimize the circuits, as you will see. And then we're going to build combinational logic circuits. I already said the last one, minimizing logic circuits. Okay. These are some reminder slides. We discussed that all computers, all modern computers at least, are built using the same building blocks. And remember, this is just to jog your memory. These are some of the topics that we delved into yesterday. We talked about general purpose versus special purpose, the differences between them. So this is an example of a trade-off analysis, right, that we did at a high level, at least. And then we jumped into introducing transistors. And we discussed transistors at an abstraction level that's going to be useful for us in the rest of this course. We don't talk about the analog operational properties of the transistors, but we really talk about the transistors as a digital substrate. You turn it on or off. That's it. And that's all you need to know, really, in this course. And we talked about different types of transistors, N-type and P-type. And we said that N-type is turned on, meaning when you apply, it turned on when you actually apply high voltage to the gate, meaning it acts as a piece of wire. It's turned off if you apply low voltage, 0 volts to the gate. It acts as an open circuit. The wire is broken, basically. This is a very nice abstraction to enable building digital circuits. And we showed that you could actually light a bulb by replacing the volt switch with a transistor, right? N-type or P-type. Okay, and then we started building logic gates. You remember this picture from one of the later slides yesterday that we covered yesterday. We built the inverter first. And you can see that inverter requires 2 transistors, P-type connected to the power rail, high voltage, and N-type connected to the ground rail, which is low voltage. And this is a structure that we introduced. I'm going to talk about that again. Complementary metal oxide semiconductor. You have PMOS at the top and NMOS at the bottom. And this inverts the signal, single input signal, to the opposite value. If it's 3 volts, you get 0 volts. If it's 0 volts, you get 3 volts. But for later, we're going to basically say 3 volts corresponds to high voltage, a logical 1, and 0 volts corresponds to a logical 0. This could be encoded in a different way, of course, exactly the opposite way. You need to encode in one way. And if you encode it logically, you basically get an inverter in the logical domain. Makes sense, right? And then we built a NAND gate, which essentially is AND and an inverter on behind it, if you think about it that way. And this is the function. And we call this the truth table, if you remember. Truth table specifies the operation of a circuit by enumerating all possible combinations of the input. In this case, you have 2 inputs, A, B, and which means that each of them can take 2 logical values. So you have 2 to the power of 2 combinations, 4 combinations. For each input combination, you specify what the output bit should be. This is a 2 input, 1 output function, as you can see. And we can build M input and N input functions, as we will see later on today. These are very simple, basic building blocks to begin with. And we said that if you want to build an AND gate, you need to start with NAND and then add an inverter behind it. And today we're going to go a little bit deeper as to why that is the case. If you actually read Harris and Harris section 1.7, probably you figured out why this is the case, why we cannot build an AND gate with only 4 transistors. Because if you actually know the operational principles of the transistors, just like a perfect switch, you should be able to build an AND gate with only 4 transistors, but we cannot because they're not perfect switches, as we will see. So an AND gate is essentially a NAND gate plus an inverter added to it. So the inverter actually inverts this output over here. As you can see, this output here is the inverted version of what you get out of the AND gate. And these are the logical I guess, module level pictures of these basic building blocks. And as I mentioned yesterday, the bubbles are always inversion. Bubble always says inversion. And we're going to have some fun with bubbles today. We're going to do some bubble pushing. Does anybody know about bubble pushing? Okay, you will see. It's fun. There's actually a lot of fun you can play with. You can do with gates, but we won't have enough time. So this is the last slide I finished with. I basically said this is the general form we use to construct any inverting logic gate. This is CMOS gate structure. You have two networks. You have a PMOS. You have one network that's made up of PMOS transistors. It could be transistors in series or in parallel. But these transistors are connected to 3 volts because PMOS transistors are good at pulling up the output. They're very bad at pulling down. You never connect them to the ground. You always connect them to the top, which is, in this case, 3 volts. And then when the transistors are in parallel, the network is on. When the transistors, if one of the transistors is on, that's the operation of parallel. If you go back over here, for example, these 2 transistors are in parallel. The PMOS transistors are in parallel. And the 3 volts get connected to the output only if one of them is on, or both of them are on. Well, not only if one of them is on, or if at least one of them is on. Okay. When the transistors are in series, the network is on only if all of the transistors are on, just like we have seen here. These 2 NMOS transistors, both of them need to be turned on so that the output is connected to 0 volts. And you can see that in the truth table over here. Both of the inputs should be 1 so that these NMOS transistors are turned on so that the output gets pulled down to 0. And these are complementary, meaning when both of these are on, both of these are off because of the way we introduce the transistors. PMOS transistors get turned off when you apply 1 to their gate, and both of these are off. So this part of the circuit gets disconnected from the output. Okay, hopefully this makes sense, right? Okay, so I already said actually what I was going to say over here. Exactly one network should be on and the other network should be off at any given time. Because if you violate this, if both networks are on, meaning if 3 volts over here gets connected to the output, and also 0 volts here gets connected to the output, then you're in trouble. Because this is called a short circuit and you'll get likely incorrect operation. This is basic electrical principles again. If both networks are off, this is actually not that bad. Meaning neither 3 volts nor 0 volts gets connected to the output. This is also called output is floating, meaning output is undefined. In some cases, this may be acceptable, as we will see later on. In many cases, if you're going to use that output for something, it's not acceptable. But if you're actually going to use that output to load a wire, it could be acceptable. We're going to see tri-state buffers later on. Tri-state buffers actually operate this way. So the first is very bad. You will burn the circuit, perhaps. The second is, depends on what you're doing. If you know what you're doing, then this may be okay. Does that make sense? If it doesn't make sense, wait until the tri-state buffer later today. Okay, so why do we have this structure? You may say that, okay, I could build a much better AND gate. Did anybody try? Yes.
You could have the PMOS in series and the NMOS.
Exactly, yes. You could have the, let me see. You can have the NMOS in series connected to the 3 volts, and you could have the PMOS in parallel connected to the 0 volt. If you think about it, let me see. I think I'll do this. Can someone help me to do this? I don't know why it's going this way. Maybe you can do the computer. Let's see if we will get it right. I hope so. So this is 3 volts. I want to build an AND gate, right? And this is my NMOS. This is my output. And this is my PMOS. I never want to do this probably, but I'll do it. So AND gates should give you a 1 if both of the inputs are 1. So this is A, this is B. I also have A here, and I also have B here, sorry. And then this is ground. And this is your output Y in our terminology. Now this should be an AND gate, right? because the output is, assuming these are perfect switches, output should be equal to 3 volts only if A and B are 1. Otherwise, it should be equal to 0 volts, right? And it works. It's complementary also, except the problem is these are not perfect switches. This transistor, this is NMOS that I used over here. I violated what I said earlier. I should use only PMOS connected to the high voltage. This NMOS is terrible at pulling up the voltage because of the underlying operational characteristics, which you should learn if you actually design microelectronics. It will pull up the voltage to maybe 1.5 volts if you're lucky. And these are actually also terrible at pulling down the voltage. So when one of them is 0, then this actually also doesn't pull down very well. So maybe you get, I don't know, some voltage that's not necessarily 0, right? So this is good to understand. If you don't understand the underlying operational characteristics, then you would basically, if you treat the transistor as a perfect switch, you would basically not understand this, right? You can build an AND gate like this. But because of the way transistors cannot work as a perfect switch because of their analog operational characteristics, and the reason is really whether they transmit holes or electrons, as I will mention, but I will not go into a lot of detail because it's really analog circuitry after this point. This AND gate is not acceptable, at least using PMOS and NMOS transistors. Does that make sense? Okay, now we can switch back. I hope I can figure this out. I guess you can help me. So probably you were suggesting this sort of AND gate, right? It's a good try, but not in this technology. You can come up with maybe some other technology where you could do it, but people couldn't come up with that yet. Okay, this is what we need AI for. AI basically, I say switch to this, and then it should be able to switch, right? Okay, any questions? So, okay, this is what I said over here in this slide. PMOS transistors pass ones well, but zeros poorly. Holes carry charge, and holes are good at passing ones, but not zeros. Similarly, NMOS transistors pass ones poorly as a result, because electrons carry charge, and electrons, essentially they're very bad at pulling up the circuit. Okay, you don't need to know this in detail, but I wanted to show you that if you try to be clever with the underlying circuitry, if you don't know how the underlying circuitry really works, you may come up with something that doesn't make sense, right? So that's why you need to be careful. You really need to know how the underlying thing works. That's why what we did was an abstraction, and the abstraction was it's a switch under some conditions. Okay, that's why we built this AND with 6 transistors as opposed to 4 transistors that I tried earlier. And if you want to know more about it, you can read section 1.7, or you can take a microelectronics design course. Okay, so let's dig a little bit deeper. I'll ask you a question. Which one's slower? Transistors in series that are connected in series, or transistor in parallel? Who says series is slower? Okay, that's good. Who says parallel is slower? Nobody, so you win. So series is slower because it's longer, right? You have longer wire, and longer wires lead to longer resistance. And resistance is what leads to latency. The question is, how do you alleviate this latency? There are actually tricks people play, again, using underlying knowledge of transistors. I'm not going to go through this, but this is interesting to think about. People build, for example, this is a NOR gate, 4-input NOR gate, that you can build with only NMOS transistors, without a PMOS. Actually, there is a PMOS transistor over here, but it's very weak. People used to do this in the past when it was difficult to manufacture PMOS transistors. Make sense? Okay, you can convince yourself that this works as a 4-input NOR gate, and it does actually, but today people don't do that as much unless they're really constrained by area or something. This is actually good for area also, as you can see. Yes?
What does it mean for a transistor to be weak?
Weak meaning basically, it doesn't, that's a good question basically. It doesn't get turned on with quickly. Does that make sense? Yeah. There's still some latency over here, but it's not as much latency as 4 PMOS transistors. Okay? Okay, but again, This is for fun. You can play tricks. I'm not going to ask you anything related to this. It's good to know. Okay, let's talk about power consumption. This is the last thing I'm going to talk about at a lower level because it's very important, I think. So whenever you actually build a transistor and power it on, it consumes power. Whenever you switch the transistor, apply some voltage to the gate, it actually consumes dynamic power. So there are two types of power consumption, dynamic power and static power. Dynamic power is the power that's used to charge the capacitance as signals change. So essentially, a signal changes from 0 to 1 or 1 to 0, for example. Right? So this is the basic power equation. How many of you have seen this before? Dynamic power. Some of you. Maybe not that many. How many? Here's your. Okay, not that many. Okay, fine. But basically, every circuit has some capacitance because you have wires and gates. It could be one or more transistors. An AND gate, for example, can be represented with some capacitance. And then you apply some supply voltage to it, as we have seen. There's also some frequency at which you change the values. This is actually going to be the clock frequency later on as we introduce the clock in sequential logic. And power is really a function of capacitance times the square of the voltage times frequency. Again, this is based on laws of physics. So if you have higher capacitance, meaning higher loading, lots of transistors on the output connected to the output, you will consume higher power. If your supply voltage is higher, you will consume higher power. If your charging frequency is higher, you'll consume higher power, right? Usually, if you want to increase the frequency, you also want to increase the voltage so that you can actually do that fast switching, meaning that frequency is actually a function of voltage. So voltage actually cubically affects power, meaning if you increase voltage, you get a cubical effect on power. So voltage is very bad for power in general. You want to reduce, this is why existing circuits try to reduce voltage as much as possible, as we have mentioned yesterday. Yes?
But isn't power also voltage times current? And usually when we try to switch the transistor to current, right?
Well, that's the static power. That's the voltage times current. So we're talking about dynamic power. When you're dynamically switching, this is what happens. But when you're not actually applying any switching, you're not changing the values in the gate. When signals don't change, you still consume some power because the transistor leaks. It's not a perfect switch. Another example of this, basically, there's some current that's always leaking inside the transistor because it's connected to either high voltage or ground. And this is the static power that you consume. The voltage times some leakage current that you have. So the overall power that you consume is a function of dynamic power, how often you switch. If you're never switching, something is leaking. For example, in my cell phone, in my pocket, I'm not doing anything. Hopefully it's not doing anything also. But if it's turned on, it's leaking. So the battery will leak over time because the circuit is actually draining static power consumption, essentially. Okay, I already said this, I think. So this is good to know. Energy consumption, probably you know from basic physics that energy is an integral of power over time. You basically do that to figure out how much energy you consume. And you need to include both static power and dynamic power. Clearly, dynamic power depends on what you're running on the gates, right? If the Again, I don't necessarily need to go back to program, but if you think about a microprocessor, the microprocessor consists of many millions of gates. And the program is exercising many of these gates. And every one of them is consuming dynamic power if they're switching. Also, every one of them is consuming static power at the same time when they're not switching. The total energy consumption you get is the combination of those powers over time. Does that make sense? Okay. It's good to know because this is going to be important. Well, it's clearly very important today, right? This is also one of the reasons why it's good to reduce the circuits, because as you make the circuits larger, capacitance becomes larger, and clearly capacitance is an effect. And it's also good to reduce voltage. And ideally, you want to reduce frequency, but frequency has implications on performance as well, as we will see in sequential circuits. Okay, so these are some common logic gates that I added some more over here. We saw, I guess we didn't see the buffer, but buffer is essentially a buffer. It amplifies the signal, because sometimes signals lose strength when they travel, and you may not want to amplify them. But it's logically, it has no effect on the input, as you can see. Inverter, bubble, remember, and NAND, or NOR, and there's XOR. Probably you've seen XOR also. Yes? Okay. Okay, we're going to see XOR more later, and then there's XNOR, of course. These are how they're shown in module level, pictorially. We can build larger gates. We can extend the gates to more than 2 inputs. We can do a 3-input AND gate, 10-input NOR gate. This is an example from your book that shows a 3-input NAND gate. Again, you can make it bigger and bigger, but the trade-offs that we discussed apply. So if you keep adding more transistors in series, that's not very good in terms of the latency of this gate, right? If you have a 10-input NAND gate with 10 transistors in series, the latency will be high. Yes?
I think there should be some kind of self-induction that opposes the current. Enough to include it in that.
Not as significant, yes, but this we can discuss more. Okay. Any questions? Yes. I mean, they could. So especially when you're powering things up, for example, you may have some current spikes, and they actually may have impact on. Certainly, they have impact on the lifetime of transistors. No question about that. So high voltage, high current, those actually affect reliability of the circuits, especially when the circuits are very small. So no question about that. But these are very good questions that we're not going to get into. We may get into something similar at some point, but not yet. Yes? Oh, I see. Well, I think you need to, you need to keep track of it. Normally, your book doesn't do a good job in this one, but normally what I do is, when a wire branches from another one, I put a black circle there. Your book didn't do it, but here you need to traverse it. Like B goes here, A goes here, and C goes here, right? Yeah. That's a bit unfortunate, yes. Okay, any other questions? Yes.
When you increase the size of the inputs, because I think, wouldn't it be better to simply have like multiple AND gates and then one kind of puts them together?
Yeah, exactly. So basically, as opposed to building a huge AND gate, like 10-input NOR gate, maybe it's better to have many 2-input NOR gates and create a NOR out of them, right? That's what you're saying. Yes, exactly. Because the latency that you get over here may be much worse, and the power that you get over here with a huge NAND gate may be much worse than a 2-input NAND gate. But these are very good things to think about, which we will not necessarily go into. If you want to go into all of these, then you need to actually get a proper logic design course. And logic design takes multiple semesters to study in electrical engineering. But very good questions. You guys are touching into all important topics in how you design microprocessors. Robustness, latency, power. Okay, I'm moving on. I'll go through this relatively quickly because we discussed Moore's law with some folks yesterday. Essentially, what we discussed, transistors have been getting cheaper. That's what Moore's law is about. You can put more transistors on a single chip, assuming the area is constant. Right. And this is dictated by Moore's law, which I'm going to assign you as an optional reading. And this is Moore's original picture, where he plotted the year of fabrication and number of components per integrated function on a chip. And he basically figured out that it goes like this. This is log scale, as you can see. So it's growing exponentially. And this is another picture that I like, actually, where he plotted circuits that are manufactured in 1962, 1965, and 1970. And he basically showed that the relative manufacturing cost per component, you can think of component as a transistor in this case, has a sweet spot. So in 1962, that sweet spot was here. If you actually manufacture 10 components, 10 transistors, let's say, you would minimize the cost. In 1965, you would actually reduce the size and as a result, you could actually put more components at lower cost. And in 1970, you could actually put even more components at lower cost. Make sense? So basically, by reducing the size of the transistor and other circuitry, you can put more components in the same area. And these are some recent pictures that show that you can actually get many more transistors. Today, actually, we're at the level of 60, 70 billion transistors per chip. Okay, I'm going to let you read the paper. This is actually a nice paper, an old paper, as you can see, but it's good to read some fundamental papers. It's only 3 pages. And you can see that he is predicting over here by 1975, 10 years later, economics may dictate squeezing as many as 65,000 components on a single silicon chip. Today, we're at almost 75 billion. Okay. And also, there are some interesting things that he mentions. Will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? This is what we had in early 2000s or so. People actually were putting too many transistors, and power was a huge issue. And as a result, people moved to more lower frequency chips that do parallel processing. GPUs are kind of an example of that. Okay, so how do we keep Moore's law? Essentially, how do we put more transistors? How can we make the transistors smaller and smaller? This is actually a huge topic today. Again, this is below our level of abstraction, but it's good to think about it because a lot of things that we're going to do in digital logic and architecture builds on the transistors and these low-level components. So we want to manufacture smaller transistors and structures. It's difficult today because some structures are already a few atoms in size. To be able to do better, we want to use materials with better properties that can be manufactured much smaller. So people have actually innovated a lot in this area. I'm not going to talk about that. Making sure materials are compatible is a challenge here. Precision manufacturing is extremely important today. There's a lot of geopolitical implications also, unfortunately. But people try to use light at least extreme ultraviolet light to etch or pattern very small structures on silicon. And you need machines like what I'm going to show you later on. And there's a lot of innovation at these levels. And creating new device technologies is also important. These are different types of transistors, basically. We've seen one NMOS and PMOS, but there are many, many different types of transistors that operate on similar principles, but not exactly the same principles. And again, so there's innovation at the levels that we're not going to cover. That's the purpose of some of these slides over here. So if you're interested in this stuff, then you should definitely think about like microelectronics design, fabrication technologies, precision manufacturing, etc. I'll recommend you a 5-minute video on transistor innovation. That's very high level, but I like this picture over here. This is the relative size of a transistor that was manufactured in 1971, I think. This is the first Intel. And this is the relative size of a transistor today. You cannot see it. Okay. And these are some of the machines that are used today to manufacture things. Again, I'm not going to go through the detail because this is not our subject, but it's fascinating, the amount of engineering and innovation and science that goes into these machines so that you can actually, these are huge machines. It's basically, the goal is really to get the light to the right place and to the right precision so that you can etch one of these really small transistors at the right place at the right time on silicon. So you design a huge machine and infrastructure for that so that you can do this at the nanometer level, which is fascinating, I think. Again, if you're interested, there's a lot of information, especially the IEDM conference talks about some of these things, but then there's more at other conferences. So my point is innovation at the bottom actually enables computing a lot, even though we sometimes forget it. Sometimes our thinking is clouded by this high-level stuff like AI. Yes, AI, but what is it based on, right? It's really based on all of this innovation that has happened. And if none of that happened, that AI wouldn't happen also. So it's good to think about the stack. Okay, that's why I mentioned this. There's plenty of room at the bottom yesterday. Okay, so this is your extra assignment too, because it's so important. Don't use AI. I want your personalized review of Moore's paper that was written in 1965. It's only 3 pages, actually maybe 2 pages or so. Does that sound good? All right. Okay, any questions? Okay, now let's jump into combinational logic circuits because we've covered the basics. We can now build logic circuits. We actually built gates. Our next step is to build some of the logic structures that are important components of the microarchitecture of a computer. We're going to build the microarchitecture after this. A logic circuit is really composed of inputs, outputs, and a specification. There are two types of specification, which is functional specification. Timing is not important. Everything happens immediately or with some latency. We're going to talk about functional. I know what's happening here. Internet connection unstable. Everything is good? Maybe. As long as it's online, it's fine, I guess. So functional specification describes the relationship between inputs and outputs. Timing specification describes the delay between inputs changing and outputs responding to them. We're going to have a special lecture on timing, which is important, and that's going to be the only lower level lecture that we will have. Today, we're going to be functional. So there are two types of logic circuits. One is combinational logic, the other is sequential. Combinational logic is memoryless. Basically, you don't remember what you have done. You take the inputs, you transform them to outputs, but there is no memory. Outputs are strictly dependent on the combination of input values that are applied to the circuit right now. That's why it's called combinational. It's basically based on the combination of input values. This is also called combinatorial logic in some books, but you don't need to worry about that in your books. Later, we will learn sequential logic, later meaning next week. It has memory. Structure stores history, and this can store data values. Clearly, sequential logic plus combinational logic together is very powerful, as we will see. And in sequential logic, outputs are determined not only by the combination of the current inputs, but also by historical things that are stored in the circuit, as we will see, like in memory. Okay? So now we're going to go into Boolean algebra, and I may go fast, so stop me if I'm going too fast, because I'm assuming that you've seen a lot of this. So functional specification of outputs in terms of inputs is essentially how you specify a circuit based on inputs, right? So what do we mean by function? Of course, function is really a unique mapping from input values to output values. We've seen functions earlier. AND is a function, OR is a function, NOT is a function, right? All of those are functions. The same input values produce the same output value every time. That's good. There's no memory. Output does not depend on past input values, okay? So this is an example of a full one-bit adder. We're going to see this more. But if you would want to do one-bit binary addition, you add two things, A and B, and then you have a carry in, and you compute the sum, and you also compute the carry out. Just like you do decimal addition, you do binary addition, right? You've seen binary addition before. And this is actually the functional specification. It turns out sum is A XOR B XOR C in, and carry is a three-input majority function, A and B, or A and C in, or B and C in. This is really the majority function of 2 out of 3 values, as you can think about. But you can also specify this as a truth table and optimize it, as we will see soon. Okay, there are simple equations. We've already seen these, so I'm going to go through these relatively quickly. This is NOT, this is AND, this is OR, and we've seen representations also, pictorially, gate representations. And this is the person who's responsible for the algebra that you've learned. Boolean algebra is the algebra on ones and zeros with AND, OR, and NOT operations. So you start with some axioms. There are some basic things about objects and operations you just assume to be true. We're going to see some of these. You've probably seen this already, right? Okay, good. That's why I'm going fast, but stop me if you're, and you'll study this. You'll have exercises about minimizing things, as you will see in homeworks. And we've asked questions in the exams in the past also. These are the easy questions, I would say. We derive some laws and theorems. These allow you to manipulate Boolean expressions. And also, importantly, and this is the reason why we're really studying it, this allows you to simplify Boolean expressions. You may have a very complicated Boolean expression. If you simplify, and if you actually implement it using gates that are at the level of the complexity of the equation, it may be a very expensive circuit. But if you actually simplify it, the circuit will be much smaller, as we will see. And then we can derive more sophisticated properties useful for manipulating digital designs, represented in terms of Boolean equations. Basically, because we built everything on top of this digital abstraction, 1 and 0, and we can build gates that are able to manipulate things with AND, OR, and NOT operations, we have an algebra that can specify the operation of this hardware, essentially. And this is very nice, because this is really the theoretical basis of how you can design hardware and how you can optimize hardware and how you can reduce the size of the circuit. That's why we're talking about this. And interestingly, this theoretical basis and all of these laws and theorems enable you to automatically design hardware and automatically optimize. This is called electronic design automation. You can specify a function, and that function is specified in terms of a truth table, and a computer program goes through that truth table and generates hardware completely. Of course, you can specify things at a higher level also, perhaps like a computer program, and as long as you can convert it to some truth table form, then you can actually design a circuit for it automatically as well. It's fascinating, I think. Okay, that's why we're covering it. Okay, so probably you've seen a lot of this, but let's see. There are only two elements in the Boolean algebra, 0 and 1, and they're not equal to each other. Result of AND and OR stays in the set you start with. There's commutative laws, A or B is the same as B or A, and that applies to AND also. There are identity elements, A or 0 is A and 1 is A. There's distributed laws, basically, OR distributes over AND distributes over OR also. That's good. You can convince yourselves of these. These are axioms. You can prove them. Yeah, exactly. Complement is basically, there's a complement element, and ORing with it gives the identity element. For example, A or A bar is 1. Either A is true or not A is true. That's logic, basic logic, right? And A bar cannot be true at the same time, right? Basic logic again. So duality, how many people have seen duality before? Maybe. All the axioms come in dual form. Anything true for an expression is also true for its dual. So any derivation that you could make that is true can be flipped into a dual form, and it stays true. So more formally, this is what you do. Actually, it's better shown with an example, but a dual is formed by converting every AND operation to an OR operation, every OR operation to an AND operation, every constant 1 to a constant 0, and a constant 0 to a constant 1. But you don't change any of the literals or play with the complements. So if you look over here, this is one equation, and this is the dual of it. And both of them are true. Again, you can convince yourself, but this is what I did. Essentially, I followed these rules. Okay, let's take a look at some of these interesting duals. So X or 0 is X and 1 is X. So this is really the dual, okay? X or X is X. This is something you can simplify, right? You don't want to build an OR gate for this, for example, right? That's true for AND also. Okay, X bar is X as you expect. Okay, commutative law is also a dual actually, as you can see over here. Okay, so there are some other useful laws. Associative laws, we already discussed. Order of parentheses don't matter. Distributed laws, we also discussed it, but again, these are duals. Let's take a look at these simplification theorems a little bit. So X and Y, or X and not Y, is equal to X, because you can actually prove that, right? And then the dual of it looks like this. It's also X. This is actually very interesting. X or X and Y is actually equal to X. Again, you can convince yourself of it. I'm going to do that in the next slide. And dual of it is also true. And again, there's another one over here that I'm not going to go through. These are actually useful for simplifying expressions. So whenever you see something like this in a circuit, you can reduce it to X. And again, real programs that go through circuits to optimize things do this, as we will see later on, but we're not going to build that program. If you want to build that program, take a logic synthesis course. This is called hardware synthesis or logic synthesis. You basically optimize circuits. Okay, let's prove some of these. So this is the theorem, X and Y or X and Y prime is X. You first distribute X, take out X essentially. X is distributed over Y plus Y prime. And clearly Y plus Y prime, Y or a complement of Y is 1. And then X and 1 is X, right? Okay, I did this one. You can do the other one again very similarly. And this is what you get. So clearly you can prove this, right? So there's no magic again. De Morgan's law is actually useful, as we may see. How many people have seen De Morgan's laws? Okay, that's good. So I'm going to go through this relatively quickly again. Basically, this is what it says. You can think of this as a transformation, right? You have a function A or B or C. You take the complement and complement twice. A or B or C means at least one of A, B, or C is true. And De Morgan's version of it says it is not the case that A, B, C are all false. So it's logic again, basically, right? You can express things this way, or you can express things this way. Now, why are we bothering through this? Okay, now we've gotten to the interesting part. These conversions are useful. They're basically conversions between different types of logic functions. They can prove useful if you do not have every type of gate, or if some gates are more desirable to use than others. For example, you've designed an extremely fast NOR gate, as we have seen earlier, maybe pseudo-NMOS NOR gate, and you want to use it all the time. You want to convert everything to NOR. You go through these transformations to convert everything to NOR gates. Make sense? Okay, that's the idea basically. For example, NOR is equal to AND with inputs complemented. Now we're going to do some bubble pushing. So this is a NOR, as you can see, but it's also AND with inputs complemented. So what do? One fun way of doing this is actually you take this bubble, you push it to the inputs, the bubble goes to the inputs, and you change the gate from OR to AND. Sounds good? That's bubble pushing, basically, if you haven't seen it before. NAND is equal to OR with inputs complemented also. So this is NAND. And you take the bubble, push it to the inputs. X and Y both get bubbles, inverted, and then change the gate to OR. Now you get OR with two complemented inputs. Make sense? These are equal, basically. Now, your trade-off is if you designed a very nice one of these gates, you pick that, and you actually try to match your Boolean equations so that you actually maximize the use of the gates that you really need, that you really want to use. Okay? That's why these are useful. Okay, now let's talk about using these Boolean equations to represent a logic circuit. I think some of this is already clear, but we're going to go through some formal way of doing this. How many of you have seen sum of products form? Okay, good. Maybe some of you have seen, but I didn't see a lot of hands yet. So basically, we want to represent the function of a combinational logic block, meaning functional specification, and we want to methodically transform the function to simple functions. We want to have a good starting point for everything, because these different things can lead to different hardware realizations, and we want to enable logic minimization or simplification from a common basis, if you will. And we want to automate this process, as I discussed earlier, and I already mentioned these names. So the issue is different Boolean expressions lead to different logic gate implementations, meaning different hardware, area, cost, latency, and energy properties. So where we start with is really standardized function representations, so that we can actually do this very methodically. These are called either sum of products form or product of sums form. These enable a single, universally agreed on way of representing a Boolean function, starting from its truth table. This is also called canonical representation. I'm going to give you examples. So sum of products form, let's take a look. Assume that you have a truth table of Boolean function f. Maybe I'll just give you an example. So this is what a function looks like, right? These are 3 input, 1 output function. If you want to represent it as a sum of products form, you find all of the input combinations. These are all going to be called min terms, for which the output function is true. Basically, you find all of these. There are 5 of the input combinations. And you express the function that way. Input combination ABC is 0, 1, 1. So for this function to evaluate to true, for the output to be true, either ABC should be 0, 1, 1, or it should be 1, 0, 0, or it should be 1, 0, 1, or it should be 1, 1, 0, or it should be 1, 1, 1. This covers all possible cases under which the function will evaluate to true. And that's how we represent it, basically. F is equal to 1 if A bar B C is true, or A B bar C bar is true, or A B bar C is true, or A B C bar is true, etc. Right? So let me finish this and then we'll take a break. Does this make sense? So this is very simple, as you can see, but this is a way of representing function. Essentially, F is in a very standardized way. F is the OR of all input variable combinations that result in a 1. And all Boolean equations can be written in SOP form. This is the maximum, kind of a maximum, it's not a maximal form, but it really includes all input combinations with all literals. Okay, let me define quickly. Complement, you already know what a complement is. Literal is a variable or its complement. Implicant is a product or AND of literals. These are some examples of implicants. Min term. Now this is important. This is a product AND that includes all input variables. And sum of products forms always include min terms as defined over here. Max term, it's really the sum or that includes all input variables. We're going to use this in product of sums. So essentially, a truth table is a unique signature of a Boolean function, but it's an expensive representation. A Boolean function has many alternative Boolean expressions. So if they specify the same thing, why do we care, right? Different Boolean expressions. The reason we care is different Boolean expressions lead to different logic gates, different costs. That's why we want to start with a canonical form and minimize it as much as possible. So I've already said this, but let me find a good place to finish over here. Each min term is a product of literals over here. Each min term is true for that row only. I think actually the function over here, if you already specified it like we said with min terms, these are min terms. Min term is each of these values that evaluate to true over here. And the function evaluates to true if any of the products or any of the min terms causes the output to be 1. So you can verify this. If you apply input 1, 0, 1, it activates this term, and you get a 1 at the end, even though all of the other ones are 0. Okay, I already said all of this, so you can. These are for your thing. I'm going to finish with the shorthand because the shorthand is important. So if you agree on the order of the variables, you can represent a function much more simply than a truth table. You can enumerate each row with a decimal number that corresponds to the binary number created by the input pattern. So what does this mean? If you look at the order is increasing, right? The 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. And 1, 0, 0 is decimal 4, if you think about it, 1, 2, 4. So this is called min term 4. So if you want to specify this function, a 3-input function, you can specify it in terms of which min terms evaluate to 1. In this particular case, min terms 3, 4, 5, 6, 7 evaluate to 1. And you can use a summation notation. So basically, you don't need a truth table to evaluate a function. You say, this is a 3-input function, and these are the min terms that evaluate to 1. And this is how I compress that truth table into this thing. Makes sense, right? You need to know how many inputs you have in the function, of course. 3 input, 1 output. Okay, so this is a short-term notation, basically, as you can see. Now, what you can do is, you can, if I give you this function consists of min terms 3, 4, 5, 6, 7, you can figure out exactly what these are, because it's a 3-input function. Without looking at the truth table, you can actually say, this is my function. And then you know that this is not a minimal form, clearly. You basically go through minimizing using Boolean equations. And this evaluates to A plus BC. Again, you can convince yourself, I'm going through this relatively quickly because this is Boolean algebra, which you have seen. But what you have not seen is an agreed upon way of canonically representing a function in sum of products form. And this is the realization of the function. If you realize the function using all of this, which is the agreed upon way, which is the basis of transformations to begin with, it's very expensive, but if you actually simplify it using different methods, one of the methods is actually using Boolean algebra, axioms, theorems, all of the laws that we discussed, you'll get this one. Okay, so this is a good place to stop. I'm going to continue and finish this, and then we're going to talk about combinational logic. So let's be back at, I guess, 1 minute after the bell rings, and then we'll continue. Okay.
Do we need to discuss anything sometime soon?
I don't know. You tell me.
Probably not.
Okay. Okay, let's get settled down. People are coming in. Let me see. Okay. So we're talking about SOP form, sum of products. And I think one thing I should emphasize is you can write a function like this, and this is a single input. You need to specify how many inputs there are in the function. Otherwise, at M3, you don't know what it's referring to, right? In this case, if I tell you I have a 3-input, 1-output function, if I tell you that, let's see, only M0, function is equal to M0, you know that the function evaluates to 1 only if A, B, and C are all zeros, right? Makes sense. You have to know how many inputs there are. And I may have gone a little bit fast in the earlier part of the lecture because I kind of assumed that you know Boolean algebra, and I think you do, but maybe the notation is a little bit different. Some folks told me that in the past also. The notation we use in digital logic in general is the notation I use over here. You basically have dot or nothing if you want to do AND of 2 variables, and you have a plus to do OR. Does that make sense? It's different from notation you used probably in prior classes, right? So you need to get used to the notation. Sorry about that, but that's how people have evolved in different fields, maybe. Discrete math versus digital logic. Okay, so now you know how to represent. If I tell you I have a 3-input function and I have these minterms in that function, then you know exactly what that function is. You can go ahead and minimize that function basically, right? And minimization happens using Boolean algebra rules. Again, I will not go through this, otherwise we will not cover anything really interesting. Okay, so sum of products form. Actually, you could implement the sum of products form directly in logic. You could actually do a logic that looks like this. I'm not going to do that. I'm going to show you another one over here. This is another 3-input function, as you can see. It could be implemented this way. It's 2-level logic, as you can see, right? It's 1 level has AND gates. In this case, you have 3 minterms, so you need 3 AND gates. And the second level is always an OR gate for a single output, right? So you basically, the first level computes the different minterms using AND gates, and the second level ORs them. This is a perfectly fine implementation at the logic level. You could actually use the gates underlying transistors, except it's just too expensive, right? Does that make sense? That's why we go and simplify this. And if you go and simplify this, essentially, basically, SOP form is perfectly fine as logic implementation, but doesn't lead to minimal logic directly. You need to simplify it. Okay. So this is a summary of canonical sum of products that I'm not going to go through, but essentially, logically, SOP form represents the function as a sum or of all products, minterms, that cause the output to be 1. Hopefully that's clear, right? You figure out which minterms lead to 1, and you OR them. That's it. Now, product of sums is another way of representing things. I like sum of products because it's easier, but once you deal with products of sums, you can actually, once you understand products of sums, you can actually deal with it also. A formal way of thinking about product of sums is it's really the De Morgan of sum of products of f prime, meaning the complement of f. I don't like thinking about it this way. I like thinking about it as a truth table, or this way. Essentially, find all the input combinations, max terms, for which the output of the function is false. We're going to look at the other part, essentially. Not the input combinations where the output was 1. We're going to look at the input combinations that are where the output is 0. And then you end, essentially, f, or product of sum forms, can express the function as end of all input variable combinations that result in a 0. So we're going to do the same thing, except we're going to deal with the 0 outputs. We're going to take that, and we're going to say the function is 0 if any of these input combinations is 0. Any means end. If A is 0, B is 0, C is 0, the function is 0. I don't care what these are. If A is 0, B is 0, C is 1, the function is 0. And that's what this max term is about. If A is 0, B is 1, C is 0, the function is 0. I don't care about the other ones. Makes sense, right? So this is a bit less intuitive. I don't think it's less intuitive, but you need to get used to it. Essentially, the reason it's called product of sums is it's really product of these sums. Now you have ORs over here and over here. Okay. So each sum term represents one of the zeros of the function, basically. The function evaluates to false, i.e. output is 0 if any of the sums, in this case max terms, these are the max terms, causes the output to be 0. Don't get too bogged down in terminology. Everything is, I think, relatively simple over here. Okay. So basically, if your input is 0, 1, 0, it activates this max term, and that max term evaluates to 0. These max terms, even though they may or may not evaluate to 0, you get essentially 0 in the end. You don't care about these other ones. Okay. I think I already said everything over here. Anything ended with 0, 0, so output F will be 0. So this is another way of actually specifying the circuit, as you can see, right? I already said all of this, actually. It's the same thing shown in gates. Okay, so how do you write it? Essentially, you need to figure out the parts where the function is 0, or input combinations, truth table rows, in other words. If you have a 0 in the input column, it's a true literal. If you have 1 in the input column, it's complement literal. You OR the literals to get a max term, which is basically this. For example, let's take a look at this one. 0, 1, 0. You do A, B bar, C. A, B bar, C, and you OR them. Okay, that's the max term. And you add together all the max terms for which the function is 0. Okay, that's how you get it, which is very simple, hopefully. Or you just remember, you do the product sum of products and get the De Morgan of SOP of F prime, which is not how I would do it. Okay, so you can actually do you can actually have a max term notation over here also. These are the max terms associated with different combinations of inputs. And this is our short-term notation now. We use a capital M for max terms. And we can specify this function as the sum, the product of max terms 0, 1, 2. Right? Because those are the ones that lead to 0 if you saw it in the previous case. I think I've kind of said this already. Now, note that this is not the complement of the function. This is the same function that we've seen earlier. Same function where min terms 3, 4, 5, 6, 7 specify the function. Max terms 0, 1, 2 also specify the function. Right? Okay, there are some useful conversions. I'll go through these relatively quickly also. I already said this, basically, min term to max term conversion. Basically, rewrite the min term shorthand using the max term shorthand. You basically use the indices that are not already used. You can do the same thing exactly the opposite way also. These are the same functions, basically. These two specify the same functions. These two specify the same functions also. Okay. You can expand F to F prime by changing things like this. For example, this is function Prime is actually minterms, the opposite minterms, the minterms that you didn't use. And prime is, again, max terms that you didn't use. Hopefully this is clear, right? Based on the truth table, based on the logical structure, you can figure this out. Again, I'm not going to go through this because it's kind of boring. Okay. Now, interesting thing is, using Boolean algebra, you can simplify the SOP or POS form of any function in a methodical way. You start with this canonical form. Basically, you can start with a truth table to begin with, and then you turn the truth table into a SOP or POS form, and then you use Boolean simplification rules. We're going to see how to do this for full adder later, but essentially, full adder, you can start with a truth table and simplify it to these forms. Make sense? Okay. So this was the circuit that I showed you earlier. This is a sum of products form. It leads to two-level logic. We're going to see that two-level logic later on today also again. This is a simplified form. It's still in two-level logic, but it's simplified, as you can see. This is not sum of products. So if someone gives you a 3-input function and tells you, is this in sum of product form? The answer here is yes. But here, this is not in sum of product form because it's missing some literals, right? It's a 3-input function, and you know that this is missing A, and this is missing C, which means that this is not in sum of products form. Make sense? Okay. Okay, any questions? Now we're going to jump into combinational blocks. That's the Boolean algebra I will cover for now. But it's going to be useful in designing combinational blocks that we will build upon. Yes? Yes, exactly. If you simplify, you may lose redundancy, which may be bad, as we will see in timing. It's good in terms of reducing area. It may be bad if you have some errors in the circuit, etc. It's good to think about it that way. So there are always trade-offs. You cannot say something is good or bad necessarily. You need to think about what metric is it good or bad for, right? Minimizing the circuit is good for reducing area. It could be good for reducing latency. So going from here to here, clearly less area, right? Probably less latency, based on what we have seen. But you do lose some redundancy in the circuit. Maybe if there's an error in one of the bits, you will not be able to tolerate it. Or you'll tolerate it less. Okay? And with timing, we will see something else when you do the timing analysis. Okay. All right. Let's cover some combinational blocks. So we build combinational blocks to build computers, essentially. And we've seen already some of the gates. Now we're going to see more. Essentially, combinational logic is grouped into larger building blocks to build complex systems. And then we're going to add sequential logic on top of this also. But let's keep combinational for now. The reason we do this is to tame complexity. Because think about the billions of transistors, right? You cannot just look at it with transistors. You need to actually do a hierarchical design. We're going to talk about that also. So you need to group the transistors into gates. You need to group the gates into larger blocks called modules, and maybe modules into even larger blocks, right? Processors, etc., so that you can tame that complexity. So we're going to build a hierarchy. We want to hide the unnecessary gate level details so that we can emphasize the function of the building block. So we're going to examine some things. I hope you have not seen these. Have you seen decoders before? Some of you were.
In a course.
In a course here?
No.
Okay, no. No is a good answer. Anybody else? Okay, that's good. Multiplexers, full adders, and programmable logic arrays. We're going to see more, actually. This is a more complete thing. I'm not sure. I don't know if we're going to cover everything today, but let's see how far we'll get. And these are all combinational. Okay, let's start with the decoder. Decoder is fun. It basically does what it says. It decodes an input pattern. Now, what does that mean? In other words, it's an input pattern detector. You have n inputs and 2 to the n outputs. And only one of the outputs will evaluate to 1, depending on the pattern that comes as the input. Hopefully that makes sense, right? I already said this, I think. The output that is logically 1 is the output that's corresponding to the input pattern that the logic circuit is expected to detect. So let's take a look at it. This is a 2 to 4 decoder. This is our truth table. Now, if we have 2 inputs, 4 outputs, as I said, y0 is 1 only if both of the inputs are 0. Y1 is 1, and only Y1 is 1, only if the inputs are 0, 1. And Y2 is 1, and only Y2 is 1, only if A1, the two inputs are 1, 0, and Y3 is 1, only if A1 and A0 are 1, 1. Now you can see that if Y0 is raised as an output, you know that the input pattern is 0, 0, right? Now you can basically decoded the input pattern. Make sense? Okay, that's good. A lot of pattern matching circuits actually use this. Very simple, very basic, and we're going to abstract it this way. If you actually see an abstraction that looks like this 2 to 4 decoder, this is our module. And this is how we're going to attain complexity. We're not going to represent it with underlying gates or transistors. But I'm going to show you the underlying implementation with gates soon. So this means that Y3 is raised, meaning 1, if A1 and A0 are both 1. Okay? Okay, so hopefully it's simple. Now this is the gate level implementation of that decoder, or one gate level implementation of that decoder, right? And you can see I built it using AND gates, and we can invert A and B. And this is my notation. You had a question earlier. This is how you can say, based on my notation, that this wire over here belongs to this, right? That's how you go out of it, and you don't confuse these two wires over here. Hopefully that makes sense. There are other notations potentially, but basically this AND gate evaluates to 1 only if A and B are both 1. This evaluates to 1 only if A and B are 1, 0, and 0, 1, and 0, 0. That's your decoder over here. Very simple, and you can check it clearly with my pictorial representation. Okay, so hopefully this is clear. This is a 2 to 4 decoder. You can have a 3 to 8 decoder, 4 to 16 decoder. I don't know, pick your favorite number. 10 to 1 to 2024 decoder. And in modern memories, we have gigabytes and gigabytes, and they actually have decoders. So what's the function of this decoder? We can specify an address, for example. If your memory is, for example, let's say 1 gigabytes, I think that's 2 to the 30, no, 4 gigabytes, let's say, that's 2 to the 32 bits, if you will, 2 to the 32 bytes. You need a 32 input decoder, and that specifies your entire address range, okay? We'll see that later on. So a decoder basically can tell you which part of your memory to enable so that you can get the data. This is called an address decoder particularly. Yes?
I think we saw decoders when we looked at what Google uses for video encoding and decoding.
Yeah, but that's a different kind of decoder. That's an overloaded term. It could be used inside, yes, inside the circuit. This is a very basic building block. It could be used for many, many different purposes. Okay? Okay. Okay, basically the decoder is useful in determining how to interpret a bit pattern. I've given you one example. It could be an address. It could be the address of a location in memory that the processor intends to read from. You get address 8, and you want to figure out which location to read, and the decoder essentially enables that line that goes to that location. This wire, for example. In this case, the address could be 2. It's a very simple address. And you get this line, and that line actually enables you to read from that part. We will see that when we talk about sequential circuit. If you don't understand right now, it's okay. Right now, we're looking at how to detect a particular pattern. Or it could be an instruction in the program, and the processor needs to decide what action to take. So how do you encode an instruction? Instruction is usually encoded as a bit pattern. Bit pattern 000 means do an add. Bit pattern 001 means do a multiply. Bit pattern 010 means do a square root. Bit pattern 011 means do a subtract. This is how you specify instructions so that the computer can understand them. This is called encoding. And someone specifies an instruction. How does the computer recognize what is that instruction? And we will see this when we talk about instructions in architecture. You need to take, this is called an opcode. The bit pattern is called an opcode. And there needs to be some circuitry, decoder, in the processor that basically takes that opcode and decodes it. Assuming that your bit pattern is 10, it tells you that, oh, it's this instruction that I'm going to do. So it enables some logic that ensures that that instruction is executed. Make sense? This is how you detect, how you interpret a bit pattern, basically. Again, you will see this, but this is important because we're going to build on all of these logic structures to build a microprocessor, and they're all needed, as we will see. Okay, multiplexer. How many of you have seen this one? Okay, people who have taken logic design courses maybe have seen it, or something similar. This is also called a selector. It selects one of the n inputs to connect it to the output. Let's see, based on the value of a control input called a select input. So let's start with a very simple 2-to-1 mux multiplexer selector. So 2-to-1 mux has 2 data inputs and 1 select input. If the select input is 0, output is equal to data input 0, as you can see. If the select input is 1, output is the same as data input 1. Basically, it selects. It chooses one of the inputs to pass to the output. And this is the module representation of a 2-to-1 mux. These are, basically, if the select input is 0, this bit D0 becomes output Y. If the select input is 1, this bit D1 becomes output Y. These could be actually many bits. If the select input is 0, you select a 32 input, 32-bit data and put it onto a 32-bit output, right? It could be, but right now we're dealing with bits. Later, you can generalize it. Makes sense, right? Basically, you're selecting something. This is good for choosing what to do in the underlying circuitry. Okay? Okay. This is the low-level gate implementation that we will hopefully not need in the future because we know what the module does functionally, right? But this is to convince yourself that this can be realized with 2-level logic in this particular case, but it's not sum of products form. And you would recognize that because you have 3 inputs, as you can see, and we have here 2 inputs, so we've simplified it. So basically what this does is, if select input is 1, output will be B over here. If the select input is 0, output will be A over here. And you can convince yourself, again, me pictorially, choosing select input 0, this becomes 1, so this AND gate passes A. This becomes 0, so this is, let's say, 0 in the end, and A or 0 is A, right? Whatever value is of A will be output over here. Okay, that's a selector, basically. Okay, we already said this, but the output C is always connected to either the input A or input B. Output value depends on the select value or select line, also called S, essentially. So this is another pictorial way of looking at it. If you select lines are usually shown, this is a control line, usually shown, at least, this is not always the case, but usually, Pat and Patel does a good job. I think Harris also does a good job in it, with an empty arrow. Whereas data lines are usually shown with like darker arrows like this over here. Here it's white, here it's black. So this is select or control line, and this is data lines. And you pick one of the data inputs. Okay. Another way of representing this in a different kind of truth table, not just ones and zeros, is this. This is a truth table, except it uses a kind of different structure, right? You just, inputs are part of the output over here. They're not shown over here. So in that sense, it's not a, let's say, kosher truth table. It's a truth table that you can interpret as a human, but it's not a truth table the way we defined it. It doesn't have all the input combinations, basically, because inputs are over here. But it's a good way of thinking about it because this enables you to simplify things nicely from a logical perspective, right? Humans are not necessarily machines that just use ones and zeros, as you can see, right? Okay, so basically, if select input is 0, output C is A. If select input is 1, output C is B. I like this truth table. Okay. Okay, I'm going to do this task for you in the next slide. Using 2-to-1 muxes, you can actually have a 4-to-1 mux. You can do it at the gate level. You could do it at the module level. And this is the module level, and this is the gate level. And you can convince yourself that this is each one of these is a 2-to-1 mux. Now you have 2 select inputs because we want to select between 4 things, 4 data inputs. So you, log 2 to the 4 is 2. So you need to have 2-bit select inputs. And you connect S0 to the first level. So you have 2 to the 1 muxes over here, and you have the second level select using the second select input. And this S0 also propagates to here. So this is S0. It's not an output from the mux. It's the downside of your book, I guess, a little bit. And you can convince yourself that this select 0, if it's 0, selects D0. And if select 1 is also 0, you select D0 to the output. That's what we want. If both S0 and S1 are 0, we should select D0. If S0 is 1, S1 is 0, we should select D1. And you can, again, convince yourself that this works. And this is the gate level representation that I'm not going to go through. But you can see that it's very similar to 2 to the 1 mux, except, it's not 2 to the 1 anymore. It's 4 to the 1. 4 to 1 mux. Make sense? Okay. Okay. So learn muxes. Multiplexers are good. And we're going to have a little bit more fun right now with multiplexers because they enable some things that you're going to use in your FPGAs. Any questions before I move on? So now you know how to detect an input pattern. Now you know how to select an input data based on a control input. So you can actually combine these things, as we will see. When we build memories, we're going to combine these things, actually. Okay, I'm not going to get ahead of myself. So, okay, one interesting thing about multiplexers is they can be used as lookup tables to perform logic functions. And a lot of FPGAs do things like this. Okay, this is from your book. This is a logic function. It's actually a logic function that we've seen. It's AND. Y is equal to A and B. You can formulate this truth table as a multiplexer. So how do you do it? Inputs, in this case, A, B are select inputs. But then you also have some inputs that you hardwire. So if A and B are both 0, the multiplexer selects the 0, 0 input, which is hardwired to 0, ground. Sounds good, right? Only if A and B are both 1, the multiplexer selects the 1, 1 input, which is hardwired to 1, logic, 3 volts, if you remember, and Y is equal to that. So this way, we built an AND gate using a multiplexer. Pretty expensive. You don't want to do it. But there may be cases where this is cheaper. And there may be cases where this is actually useful. Does that make sense? Using a multiplexer, input is A. If A is 0, the output should be 0, as expected. That's why AND. If A is 1, the output should depend on B, which is as expected. Now you have a multiplexer that implements an AND gate in a simpler fashion. Does that sound good? Okay, so you can have fun. This is XOR. Now XOR is normally complicated, but with muxes, actually, you can make it cheaper, maybe. I don't know. But this is another way of doing it. Again, A XOR B. This function is A XOR B. If the two values are equal, you get a 0. If there is a difference, you get a 1. In fact, we're going to use this in equality checker later on. You can express it like this. If A is 0, Y should be B. If A is 1, Y should be B bar. And this is the multiplexer implementation of it. Clearly, you could implement it using AND. You could actually simplify it using the way we discussed. But now we used multiplexer logic. Sounds good, right? This is another example, more complicated one. Now, I can go through this forever, but I'm not going to do that, I guess. Basically, this is the sum of products form. This is the implementation of a sum of products form using a multiplexer. All of the inputs are here. All of the essentially input combinations are here. And you basically wire the input combinations that evaluate to 1 to 1, which is high power, high voltage. You wire the input combinations that evaluate to 0 to zeros. And then your multiplexer selects the right input combination. Makes sense when you apply the input. Okay, clearly bad idea because it's expensive logic, right? But it's doable. Now, why it could be a good idea if you want programmability. And your FPGAs, existing FPGAs actually work with structures that kind of look like this. Not exactly, but similar. In the sense that if you want to implement a function, you can specify it using a lookup table. This is also called a lookup table. In fact, what I did was a kind of a hardwired lookup table. You could make it more programmable, which I'm not going to go into right now. But when we talk about memories, you can imagine how to program it later on. But this is a 3-input lookup table. Output is 1 bit, input is 3 bits. By wiring the inputs the way you like, so that you can specify any function, any three input function. Okay, multiplexer chooses one of the 8 data inputs that corresponds to the 3-bit select inputs. And these are your data inputs. So your function is 3 bits, your output is 1 bit, and you can specify any function this way, as long as you can write what you are supposed to select based on these inputs. Now let me give you an example. I already said all of this, basically. I already said this. This is also called a 3-lot. It can implement any 3-bit input function. For example, if I want a function that outputs 1 when there are at least 2 1s in a 3-bit input, I basically figure out which of these input combinations have 2 1s, and I set the ones that have at least 2 1s to 1, which are these ones, right? 0 1 1, 1 0 1, 1 1 0, 1 1 1, and everything else to 0. And when I apply my input over here, this function will evaluate to 1 only if at least 2 of these inputs are going to be 1, right? So if I set, if I program, if you will, these input data lines to the right value, such that I specify my function, I can evaluate any function. And this is good because in an FPGA, it's called a configurable, reconfigurable system. You can implement any function. You can implement a multiplication, for example. You can specify I don't know, 4x4 multiplication as an 8-input function, and you don't need to design a multiplier for that. You can actually have a lookup table that has 2 to the 8 inputs, and you apply 2 of the 4-bit numbers as a select input to that lookup table. Make sense? This way, you don't need to build a multiplier. You do multiplication using a lookup table. Right. Okay? So FPGAs operate using these principles, and you're going to program these FPGAs. That's why I cover this, because it's really interesting and important. Okay, you can also, similarly to doing logic using multiplexers, you can do logic using decoders. So we should not make decoders feel lonely. They can actually do logic, as you can see over here. So in this case, this is A XNOR B. And using a 2 to the 4 decoder, and by adding an OR gate at the end, a decoder, what does a decoder do? It gives you the minterms, actually, right? It's good to think about that. So a decoder gives you all of the minterms because it's 2 to the 4, right? If it's 3, it gives you 8 outputs. So the minterm that's enabled actually gets a 1 at the end. Now, if you do OR, you actually get an SOP representation of that, right? Which is nice. So basically, XNOR means AB and A bar, B bar, or A bar, B bar. If any of these minterms is true, this function is true. And decoder, it gives you all the minterms. And you have the second level over here. So actually, we've seen this before. When we talked about SOP form, we kind of talked about a decoder at a Boolean level, not as at a hardware level. Okay. Now let's do more things. Adding things. So you've done binary addition, and you're reading binary addition. I'll go through this relatively quickly, but this is an m-bit binary number added to another m-bit binary number, B. It's similar to decimal addition. You go from right to left, 1 column at a time, and you generate the sum and a carry. Initially, the carry into the 0 is normally 0. Well, it should be 0 if you're doing addition. If you're doing 2's complement subtraction, which you should read in the book, the carry in is actually a 1. And we're going to see it if time permits. Let's see. So this is sum 0, which is A0 plus B0 at the bit level, and then you generate a carry in. Sum 1 is A1 plus B1 plus carry in from the 0th level, and you generate a carry out to the next level. Okay, so that's what the carries are. So truth table of binary addition on 1 column of bits within 2 m-bit operands looks like this. Basically, you look at bit by bit. AI, BI, carry I, and then you generate the carry I plus 1, and then sum I. Okay? And you can convince yourself this is the addition. Let's take a look at one of these, basically. Let's take a look at one of these. So if A is 0, B is 1, and carry is 1, the sum should be 0, because 1 plus 1 is 2, and 2 in binary is really 0. So you generate a carry because 2 is greater than the largest value that's representable in binary form. So this is what it is. So that's correct. But you can verify all of these. So if you want to do an n-bit addition, you really do n one-bit additions, right? You do this bit, generate the carry, and then you do these 3 bits, and then generate these, or this bit, and generate the carry. So it's really a sequential process, basically. Okay, and this is the SOP form implementation of an adder. We're going to simplify that later. These are all the minterms over here. Essentially, this is a decoder. And then you choose the right things in the decoder and OR them to get the carry out and the sum. Makes sense, right? I've done basically what we've done earlier, nothing fancy. This is our full adder, expensive full adder, because I didn't minimize it. The way you can minimize, and this is the module level representation. If I tell you this is a full adder, you should probably know what it's doing. Binary adder, of course. It's not a decimal adder. But now you can also realize that this is XOR. SI is really an XOR of AEI, BI, and carry I. And carry is really a majority function. And that way you can simplify it. That's one way of simplifying it. Or you can simplify it using Boolean equations. There are multiple ways of simplifying things. So I'm going to show you majority and XOR later. Okay, but now that was 1-bit adder. That's good. We can do addition in 1 bit. How do I build a 4-bit adder? As I said earlier, you basically chain these full adders. This is a single-bit adder. Carry in is 0. It generates a sum. Carry out is fed into the next bit, bit 1. It generates a carry out and sum. This carry out is fed into the next bit. This carry out is fed into the next bit. This carry out is fed in outside because we have only 4 bits. This is a 4-bit adder. Okay, you can convince yourself that it works, which I'm not going to do here. Makes sense, right? This is also called a ripple carry adder. If you heard the term ripple carry, carry is basically rippling across 1-bit adders. This is a very simple adder you can build from 1-bit adders. Now, there's a downside of this adder. Latency, right? Yes, you were going to say that? Okay. Basically, in order to evaluate the last bit, you should have evaluated everything before. This is serial, and people actually came out with many, many different ways of designing adders. Harris and Harris covers some of them. I'm going to give you one basic idea of one of the adders. Essentially, if you don't want to wait for carry to ripple through slowly, let's say 30 bits or 31 bits, you may decide a logic to accelerate the carry generation, right? Some generation is not a problem. Some generation, well, I guess some generation is a problem also because you're waiting for the carry. But basically, the critical path is really the carry generation. So if you accelerate the carry generation using some specialized logic, you can actually start some of the later sums earlier, maybe speculatively, because you don't know the exact carry, potentially, or maybe non-speculatively also. So this is a carry look-ahead adder. What it does is it basically looks at 4-bit blocks. This is a 4-bit block where each block is a ripple carry adder. But there's also some specialized logic that quickly calculates the carry based on logic equations, not based on ripple carry addition. You basically look at the adder as 4 bits, specified as a Boolean function using sum of products form, and you minimize that function, and you generate carry 4 directly from all of those bits. Make sense? Okay, keep that in mind. This is one way of accelerating carry generation. People have come up with many, many interesting ways, which I'm not going to cover. If you take a computer arithmetic course, it's fascinating, I think. Okay. Okay, programmable logic array. This is actually what's going to be an example of programmable logic that can be also configurable potentially. We call the sum of product form. We didn't talk about that for no reason. Sum of product form leads to 2-level logic. A PLA, programmable logic array, enables the 2-level SOP implementation of any n input, m output function. Programmable logic array actually looks like this, kind of, except it has programmable connections between the inputs and inputs to these AND gates, and also outputs of the AND gates to the inputs of the OR gate. Okay, so basically, you can program these connections over here. Actually, you don't have programmable connections necessarily here. You could. But in this particular programmable logic array example, you generate all the minterms, and you decide which minterms to connect to the OR gates to specify a function. Okay? You could implement hardware like this, and people have implemented hardware like this. It's expensive, but it's very flexible. as you can see. You can implement anything by programming those connections. Don't ask me about how you program the connections right now. There are different ways of doing that. In the past, people have done fuses, for example, but if you can be more programmable using muxes, for example, multiplexers is one way of programming it, but we're not going to go into how you program it, but we're going to see that you could actually implement any function this way. Okay, basically, you can implement any collection of logic functions one wishes to, assuming there are 3 inputs and at most 3 outputs over here. You have an array of AND gates followed by an array of OR gates, sum of products form. How do you determine the number of AND gates? Essentially SOP, the number of possible minterms. For an N input logic function, you need a PLA with 2 the N inputs AND gates. And each of them should specify one of the minterms. The OR gates depends on the number of output columns in the truth table. So if your function has 1 output, the other 2 gets unused in this particular case, right? Okay, so let's take a look at it. What do you do to implement a logic function? You connect the output of an AND gate to the input of an OR gate if the corresponding minterm is in the SOP. It's kind of no-brainer, right? Basically, we're implementing the SOP directly in hardware by connecting the minterm to the OR gate. And this is a simple programmable logic contract. Essentially, these connections are programmable. You can imagine how to do this using mux as multiplexers. But again, we're not going to look at the circuitry right now. You can program the connections from AND gates outputs to OR gate inputs to implement the desired logic function. There's another type of programmable logic, which is FPGAs, which we're not going to talk about, but they use lookup tables also. Okay, so PLA looks like this basically. You have an AND array, you have an OR array, inputs, and then implicants. These are all essentially the minterms, and then you have outputs. So this is one example function. Again, I will not go over this, but basically these are the programmed connections. In this case, they were nice. They added these blue things. So basically this, in this case, X evaluates to A bar, B bar, C, which is coming from here, these 3 things, and or A, B, C bar. And you can see that Y evaluates to A, B bar. Okay. Okay, and this is another way of looking at it. This is, yeah. Okay, so how do we implement a full adder using a PLA? Let's take a look at this. We saw the full adder earlier. We saw the truth table. And we're not going to change the truth table. We're going to look at the sum of products form. Sum of product form says, let me see. Okay, let me not get out of myself. Let's take a look at sum I over here. Sum I is true. Basically, you need to connect these minterms. AI, BI, carry I should be 0, 1, 0, 1, 0, 0. Well, I cannot read. Sorry, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. And you can again convince yourself that SI is connected to those minterms over here. You programmed this logic such that SI is connected to that. And you need to program the logic such that carry I is connected to the minterms where it's 1 at. And you don't need this output. And this minterm happens to be not connected to anything because clearly this minterm doesn't lead to a 1, either in carry or sum. That input should not be connected to any outputs, and we don't need this output. So this way, you don't need to design an adder. You have a PLA, you program the connections from the minterms to the OR gates, and this is your adder. Do you want a multiplier? Specify a multiplier the same way. Have a PLA large enough, and program the connections. Beautiful, right? This is another benefit of the sum of products form. You could actually do this with product of sum form also, but that's an exercise for you if you like. Okay, logical completeness. How much time do we have? Oh, okay. I think I'm going to stop here. Any questions? Any burning questions? All right, have a good weekend. I'll see you next week.